There we go. All right. Listen up, everybody. So I heard quiz yesterday went like a quiz does. So I haven't graded them yet. I just got them, but I'll have them graded for you hopefully by Monday. No guarantees because I have a lot of other stuff. I've said yes to too many things at this point. So sometime next week I will have your quizzes graded for you as fast as I can. In the meantime, some quick questions. What does SP, D, and F stand for? They don't have as very interesting names. S, I think, is sharp. P is principal. D is diffuse, and F is fine. Basically, it just comes from the way that they diffracted the light originally. The physicists who first discovered that there's different energy levels after Bohr, basically just came up with those as a way to describe how the diffraction looked. Which ties into the second one. How are we able to actually see any of this stuff? Basically, we have to get creative. You have things like, anybody heard of electron microscopes before? Electron microscope, especially a scanning tunneling electron microscope, works, but you can actually see individual atoms with that, but it doesn't really work the way a regular microscope does. You don't actually have a lens. You don't actually see things with your eyes. Basically, what a scanning tunneling electron microscope does is it has a really, really small needle that's like one to two atoms in size. And when you drag that, and they have that hanging on a wire above a surface, really, really close to a surface. And that surface is made of atoms as well, right? And so what happens is when you look at it like this so that there's room. So if you have atoms sticking up across a surface, you can actually measure that they're there by basically looking at how much resistance or how much current you're able to pass from this really, really tiny needle to the surface. It's easier to pass a current the closer this needle gets to the surface. So by measuring the current and knowing where the position of the needle is in XYZ space, you can actually get an idea of where you find orbitals, where you find these different electron clouds. But we don't actually see them in terms of with the naked eye. We then take that data and process it and turn it into a figure that looks kind of like a zoomed in, blown up version. But it's not actually seeing these things with the naked eye. Basically, chemists, because we're dealing with things that are so small, chemists and physicists have to get really, really creative with ways we can measure things because we can't just use our eyes. Even in biology, cells are big enough you can use a nice microscope and you can actually see individual organelles and things like that inside of cells. But all of that is still way orders of magnitude larger than atoms are. I don't think so. There's a lot of theoretical physics research going on with really, really small time scale laser bursts and visualizing that. So there might be something where they look at like femtosecond long laser pulses and trying to catch that in between the laser source and a target. But it's still, in that case, I guess you are seeing the photon because that's the way that our eyes work, right? And cameras work in general by a photon hitting a surface and that stimulating an electrical signal. So in that case, I guess you could see that we're seeing photons, and you can even potentially catch them in the midst between point A and point B if you're really, really careful with it. But that's been true for a long time. We just haven't had the precision with our cameras and with our light sources to be able to do that. Basically, you can think of these as flipping on a light switch and off a light switch in 1 femtosecond, so that the light flickers on for just a second. That's maybe just a couple photons emitted at once, and then trying to catch those photons in a picture before they hit another surface. So that one really just requires being really, really careful with your timing and having a really high degree of control of the timing in that case. Which also goes along with why is time change so trippy and black holes ripping space-time? Will it forever be torn or can it go back to its original state? Well, the first one is actually one of those ones where it comes down to how our brains are hardwired, right? Evolution in the universe that we live in and the world that we live in here in our solar system have led to us developing senses that are based on cause and effect. Basically, none of our senses, none of our understanding of the universe works without cause and effect, which means time is baked into how we understand the universe. Not, and this comes back to, we talked about Arrival last week. Somebody asked me about that movie. It's not, in theory, it's not necessarily a requirement for life to be conscious that it also processes time the same way we do. But as far as we're concerned, time change or time travel is always going to be trippy. I guess I read that as time travel, time change. Could just be talking about time zones, but this is the more interesting way to be, since we talked about time travel a little bit in the past. It's always going to be trippy to us just because it goes against the way that we perceive the universe. We perceive the universe with time being linear, moving constantly towards increasing entropy. If you saw something, like if I had an open 2-liter bottle of soda here and a whole bunch of soda on the ground, it would be really, really weird if you watched the soda come up off the ground and go back into the bottle and the cap screw back on. Right? That's just not how we perceive the universe. And that's so time travels will always be weird like that because it goes against everything we understand or think we understand about the universe. And along those lines, a black hole actually can disappear over time. They call it evaporation. Black holes technically are losing mass constantly. Very, very tiny amounts. But if you measure a black hole on a long enough time scale, you will actually have a measurable amount of mass disappear from that black hole. And basically, it's turning into the light that comes off of the black hole that we observe coming from the event horizon. And if you have a small enough black hole, in theory, you can actually have a black hole that evaporates completely and disappears. So it doesn't rip space-time in the sense that it's forever broken. It just behaves very differently until that evaporation happens. But a lot of the math that goes into black holes, again, goes against our normal intuition, the way we perceive the universe. And then last but not least, why is an atom radioactive when it's unstable? When those nuclei are unstable, we've talked about this a little bit, right? When they get too big, they break apart. That process is called radioactivity because it also generates a huge amount of energy when it does that. It's actually the energy that actually causes damage to our cells and causes problems like that. It's not actually the atoms splitting apart. It's the fact that when they do so, they generate so much energy and high energy light that they can cause cancer and cause other sort of physiological problems. So as a preview to what that looks like when we get to that chapter, we'll talk about this slide in more detail and actually do some math. But basically, if you look at reactants and products of a nuclear reaction, so this is uranium-235. When it gets hit with a neutron, that neutron has a possibility of kind of getting lodged into the nucleus. And when it does that, it actually causes that nucleus to split up into more pieces. So basically, you can think of the uranium nucleus as being that big, unstable mass of Legos. If I hit it hard enough with another Lego, I can get the whole thing to fall apart. And when you do that, thank you, Mel. When you do that, it actually releases a whole bunch of energy because the mass of the products is not the same as the mass of the reactant. You actually add all these things up, it looks like the same number of particles. There's 236 particles on the left-hand side, and if you add them up on the right-hand side, it's also 236 particles. But the overall mass, when we measure it, is not the same. That extra mass that disappeared, it did weigh 236 AMU, and now it weighs 235.86. that extra mass that disappeared is converted into pure energy, according to E equals mc squared. And it turns out that means it's a huge amount of energy. For context, if you burn 1 mole of butane, you get something like, let's say it's like 1,800 kilojoules per mole of butane. If you do this reaction with 1 mole of uranium, you get something like 10 to the 13 kilojoules of energy. So the difference there is, let's see, that's about 10 billion times more energetic than burning butane. We already think of burning butane as being pretty exothermic, generates a lot of heat. We're talking about something that is now way larger in terms of scale. This is the reaction that happens in a nuclear bomb. In nuclear reactors, we use uranium-238 because it won't go through this process. And in this case, and to give that context, so let's see, this is the uranium bomb. So this would have been the bomb that was dropped on Hiroshima at the end of World War II. And it was about 15 kilotons was its rating, which means it was one bomb that was, I don't know, roughly the size of this podium here. And it had as much energy released as 15,000 tons of dynamite. So 15, like a ton of dynamite right off the bat, that's a lot. We're talking 15,000 tons from a device that was this size. So it's basically radioactivity and nuclear reactions is just so many orders of magnitude larger than anything else we deal with. That's why it was a game changer and what led to the Cold War when at the end of World War II. And let's see, do we want to get into those orbitals? All right. One more, just as a follow-up to the different types of orbitals, while I was looking up the names of the s orbital, p orbital, d orbital, and all that, I found some pretty good visualizations of what the orbitals look like. Remember that these orbitals are just functions, right? They're just mathematical functions that tell you where you're likely to find an electron. And in all of these, the nucleus is going to be right in the middle. I actually don't, that's not true. That's the wrong. This figure is wrong. This is what you get when you trust Wikipedia sometimes. Where'd that other figure go that I was looking at? There's a better figure. I saw the link for quantum number. There we go. Anyway, well, I'll try and find that when we take a break in a little bit. All right, forget that figure because I don't like that one. I don't think it's right. But basically you wind up with these just really complicated looking spherical harmonics that are the different types of orbitals. We kind of talked about those a little bit though. All right, this is what we covered on Monday. We talked about periodic properties, and valence electrons, atomic radius, and ionization energy were the most important ones. There are other important variables or other important periodic trends, but they pretty much all come back to the quantum mechanics, the energy levels and electron configuration, which is why we started with that one to begin with, right? The weirdest one was that metallic character property, which is really it's a collection of other properties that all kind of make sense when you think about it in terms of orbitals. All right, the last periodic property we've talked about a little bit, but I wanted to talk about in more detail is charge. On their counting valence electrons is all well and good, but predicting the most stable charge is something that we started getting into. Last week's quiz talked a little bit about that, right? What allows us to have a stable charge? Full valence shell, right? Or all of the orbitals being either empty or full. Right, so for all of our metals, everything left of that stair-step line on the periodic table, what does that mean? What do they try to do to become more stable? Yeah, thank you. They give away the electrons, which gives them what type of charge? A positive charge. They lose an electron to become positive. And who do we have to thank for that? Mr. Ben Franklin. It's Ben Franklin's fault. All right, so when we lose an electron to have only full or empty orbitals, things get more stable. All of our metals are trying to give away electrons. Does anybody from one of their other science classes remember what you call a ion with a positive charge? Cation. You can make a cat noise, which I will not do. You can feel free to do so to remember that. I just always remember it because the T looks like a plus sign. And then what's the opposite of a cation? Anion. Cation is one of those words that I read it in a book before I ever heard it and pronounced. And so I actually thought it was pronounced cation for a long time, like vacation. It wasn't until I actually had a class talked about that I actually heard it pronounced. Yeah.
I can't help myself. With cation, another way to remember it is that cations are positive.
Pause.
Sorry.
No, that works too. How do you remember anion? You can remember it's the opposite of a cation or onion. I actually just look at the spelling. Anion is a negative ion. That works too, right? Easy enough, and it's not really a game changer if you can't remember that. It's if you just said ion, that's specific. You can always be more specific. You say it's a +1 ion instead of saying cation. So for things that are for all of our non-metals, it's pretty easy for us to predict their charge. For our transition metals, that's where all those exceptions were, though, right? So predicting the stable charges for the transition metals in the D block and in the P block left of the stair-step line, it gets kind of tricky. They oftentimes have more than one stable charge. So iron, for instance, can be a +2 or a +3. Iron +3 is more stable, but they're both stable enough that you can observe them occurring. So when it comes time to predicting which charge is going to be more stable for all those D block and all those other transition metals, we basically need to specify what the charge is on them. So we do that by just by being really specific. When we say an iron ion, we actually say it's an iron 2 ion. The way we write that is iron, and then we put Roman numeral 2 in parentheses. An iron 2 ion versus an iron 3 ion. How do we specify when something has no charge? It's not an iron ion at all. It's an iron what? Say it louder, Quinn. An iron atom. So atomic iron, metallic iron, all of those things mean a neutral iron. Iron 2 versus iron 3 are both going to be charges. In almost everything in that middle of the periodic table, we're going to specify the charge when it's got a charge. And I won't ask you to predict those because it's a lot of memorization in knowing where those exceptions occur in the D block. With 6 exceptions. The 6 exceptions, they're exceptions that make sense, is the only reason why I'm having you memorize them. Most specifically because they're never going to get a Roman numeral after their name. You say an aluminum ion, it's always the same charge. So look at where aluminum is on the periodic table. What would we expect aluminum's charge to be? +1 would empty the p orbital. +3 is better though, because then we don't have anything in the n=3 energy level, right? So aluminum is when aluminum's an ion, it's always a +3. Makes sense. There's no d orbital involved with aluminum, right? So we don't actually have to worry about it causing all those exceptions. But the 2 elements right below aluminum also follow the same rule. Gallium and indium will also always be a +3. For the same reason, because the electron configuration makes sense. Thallium starts getting a little bit weird because we start getting those energy levels so close together. It has multiple possible states it can be in. But aluminum, gallium, and indium will always be +3. In fact, So aluminum, gallium, and indium are always going to be +3. Yeah. This staircase separates the metals from the non-metals. These three are metals that always have a consistent charge when they're an ion. So, and I also want to be clear, when something is in its metallic state, that means it's neutral. So iron 3 is not metallic iron. Iron 3 is oxidized iron. It's rust, basically. When it's in its metallic state, everything is neutral. That's part of the definition of being in its metallic state or being in its elemental state. And so aluminum has a charge of 0 when it's in its metallic state. But when it becomes more stable, it becomes a +3 ion. So aluminum, gallium, indium, always going to be +3. What would we expect zinc and cadmium to do? +2. Zinc and cadmium have a full d orbital, right? They have 2 valence electrons in a full d orbital. Once it's a full d orbital, it actually behaves pretty predictably. So zinc and cadmium will always be a +2 when they're an ion. And then silver is the outlier here, but it does follow an overall trend. Silver is going to be a +1. Why do you suggest that? It's the one to the left. It's going in a predictable pattern here. +3, +2, +1. And remember, we did talk about how the electron configuration of silver is a little bit weird, right? We said that whole column, copper, silver, and gold. Silver in particular, though, its electron configuration is going to look like krypton, and then 5s1 or d10. Because it gets a chance that those ones that are in that copper, silver, and gold are in that spot where instead of putting that last electron into 5s, we can put it into 4d instead and fill up a d orbital. So silver, when it's an ion, is always a +1 because it only has 1 valence electron. Yep. It's almost always going to come out of the valence shell first. So, for instance, for iron 3, or if we look at metallic iron looks like argon, 4s2, 3d6. Yeah. It becomes a +2 ion. It's a stable +2 ion because we can pull 2 electrons out of here. It's also a stable +3 because if we take 1 electron out of 3d, we get that d orbital exactly halfway filled, which is almost as good as filling it completely. So iron has 2 possible states, electron states that make sense, that are stable. And we can, it's not that all those exceptions, all those multiple possibilities in D block don't follow our rules. It's just that we're splitting hairs when we get to that spot. Does that kind of make sense?
Yeah, question. That's only for like the 3d6 when you reach exactly halfway.
Mm-hmm.
Now, like drops like a level as in like energy level.
Yeah.
Does it drop if it's only halfway, or does it drop?
It drops part of the way. Yeah.
Okay.
I don't think it's exactly halfway, but it's the right idea. It's not as stable as getting it all the way filled, but it becomes lower in energy a little bit. All right. So, and this is also where our columns fall apart a little bit, because you'll notice that copper and gold also have a similar weirdness in the way that their electron configurations are set up, but they have more than one possible charge. Copper can be +1 or +2. Gold can be, I think it's +1 or +2 as well. Basically, there are just those other variables when we're splitting hairs. Silver winds up with everything, the stars align, so to speak, so that silver, when it's charged, will only ever be a +1. If we're talking about stable states, all of these rules all apply to like what we normally observe. There's exceptions to all this if you get to high enough energies. If you get to high enough energies, you get a plasma, in which case the electrons not being attached, not really bound to the nuclei at all, and then everything goes out the window. All of these rules kind of fall apart when we're not at Earth-like conditions. All right, so, and again, I'm not going to make you, the old school way of naming, like iron 2 versus iron 3, was you actually had to memorize a bunch of stuff. You said that iron 3, we call it a ferric ion, versus iron 2 would be a ferrous. Ion, but that still involved a whole bunch of memorizing because you had to know that ferric was a +3 and ferrous was a +2. You still had to know that iron broke apart into +2s and +3s. And copper would be cupric versus cuprous ions. So that still involved a ton of memorizing. So that's why the more modern approach, instead of we don't name things as ferric chloride anymore, we'd say iron 3 chloride instead. All right, so for now, this all makes a lot of sense when we're talking about charges. When we start talking about molecular formulas, it gets really tricky because we have to be really, really careful the way we describe these. The next, where we're going next is, well, I guess I'll get there when we get there. I won't jump the gun. All right, so if I said Cr4+, what's the name of that ion? Chromium 4 ion. If it's negative, we don't use this nomenclature because all of the nonmetals, when they gain electrons, they do it really predictably. So you can just say a nitride ion. The way we indicate something is an anion is we drop that ending. Instead of saying nitrogen ion, we say "ide" instead. "Ide" means that it's negative. So nitride ion means it's a nitrogen that's gotten enough electrons to have a full valence. So what charge would that be then? Iron, or look at where nitrogen is. How many electrons does it need to gain to fill its valence? 3. It needs to, its current electron configuration is 1s2, 2s2. When I say current, I guess when it's neutral, is 1s2, 2s2, 2p3. To fill up that second energy level, we need 3 more electrons. So nitrogen with a 3- charge, we just call that nitride. All right, so chlorine becomes fluoride, phosphorus becomes phosphide, oxygen becomes oxide. Has anybody ever heard the term oxide before? In what context? What is an oxide? Nitrous oxide, hydrogen peroxide, carbon dioxide. We have a lot of good examples here. The one I was just thinking about in general is just rust is also referred to as an oxide or an oxidation. If you put iron metal in the presence of oxygen, it'll naturally react because the iron's trying to give away electrons, right? And the oxygen's trying to gain electrons. And they wind up, kind of everybody can be happy if your iron gives up electrons and your oxygen gains the electrons, and you make iron oxide. And so when we have these names where we've got 2 elements, 2 elements, and we say both of their names, that's usually what's called an ionic compound. An ionic compound is just that case, that iron oxide example. If you've got something that wants to give away electrons and you've got something that's got too many electrons, everybody can be satisfied if we just make those charges balance out. Right? So if iron wants to give away 3 electrons, oxygen needs to gain 2 electrons. There's still a little bit of a mismatch there, though, right? And so the way we look at that is say, okay, well, if iron is going to be most stable as a +3. And oxygen is going to be most stable as a -2. How do we make it so that we have the right number of electrons have changed hands? Yeah. If we had 2 irons and 3 oxygens, that's a total of 6 electrons changing hands, right? We have to make those electrons always add up to be the same number given as accepted. So otherwise we're creating matter out of nothing, right? We try not to do that. This kind of goes against our rules for the most part. So if we do 2 of those and 3 of those, the charges add up to 0. And that means that we didn't create extra electrons out of nothing. It means that we actually made sure that everything was balanced. And we make a new ionic compound by doing that. And the way we would write that is with subscripts. These subscripts after the element symbol, after the atomic symbol, indicate how many of those ions do you have. Right? So Fe2O3 is saying you've got 3 iron ions, 2 oxide ion, or sorry, 2 iron ions, 3 oxide ions, which adds up to a charge of 0. And if we're going to name this compound, we name it by just saying both of those ions. Iron oxide, but what type of iron in particular? It's not just iron oxide, it's iron 3 oxide. All right, and here's where it gets tricky and you have to be careful with those numbers because it's Fe2O3. If you're saying the atomic symbols, then any numbers you say verbally are talking about how many of them you have. If you're saying the names, then the numbers that you hear are going to be the charges on the ions. Right, so it's iron 3 oxide, but there's only 2 irons. A really common place for people to get mixed up is when you say iron 3 oxide, they think that means I have 3 irons. We have to be really, really careful with that, right? When on your nomenclature part of your midterm, that's going to be, I won't say a third because you're going to do better than any of my classes ever have before. But a lot of you are going to make that mistake just because when you're going fast on a test, it's easy to do. So I try to overemphasize it. If you're saying the names, the number refers to the charge. If you're saying the symbols, the number refers to how many you have. All right. What if we wanted to go the other way? Instead of going from the charges to the formula to the name, what if we had the name first? The whole purpose with what we call chemical nomenclature. Nomenclature means basically the order behind names. How do you name things? The whole point of chemistry nomenclature is that every name that you give has to be unambiguous. We talked about ambiguous numbers when we talked about sig figs, right? Ambiguous was a bad thing. Unambiguous names means that anybody who knows the rules can get to the correct formula from the name and vice versa. So that we can make sure we're always talking about the same things. Right, so for, let's say that we had copper 2 sulfide. What's the formula going to be for that? You might start by writing out the ions. What's the charge on the copper ion? +2, it's in the name, right? What's the charge on the sulfide? Find sulfur on the periodic table. It needs to gain 2 electrons to be stable, correct? So -2. So in order for them to cancel out, we have one of each of them. CUS. We only need 1 copper to 1 sulfide because the sulfide wants to gain 2 electrons and the copper wants to give 2 electrons. So everything's balanced. Right. So especially when you're first getting used to this, but even if I get an unfamiliar ionic compound, and if I see the name of it, first thing I'm going to do is I'm going to write out what those ions are. Because once you know the charges on the ions, you can get to the right ratio. So what's the formula going to be for, oh, we did, how about sodium and chlorine? This is also one of the reasons why we took that elements quiz yesterday, right? So that we can do this really quickly, find stuff on the periodic table, not have to waste some time looking stuff, names and that simple stuff. Positive one. That's good. The more times we have to correct ourselves on that, the more embedded it's going to get into our subconscious. Chlorine needs to gain 1 electron. So it's minus. That was the other thing I was going to bring up. Sometimes in chemistry, we're not really picky about what these charges. If it's +2 or 2+, it means the same thing. Sometimes just the way that typesets work mean that it's really confusing. Like if you wrote bromine with a -1 charge, easy enough when I'm writing it big here, but if you're typing it, you have a non-zero probability of that -1 running, the minus symbol running into the R. Does anybody know what that's called in typeset and typing when you're typing something up if your characters run into each other like that? It's actually a technical term for it called kerning. Kerning problem means that your symbols start running into each other. And the word kerning is a good reminder of that because it looks like it might be heming, right? Is that RN or is that an M? So to avoid that issue with chemistry, since we have to deal with these superscripts, and superscripts by nature are going to be written smaller than regular symbols, you can just write one minus instead of -1. And then that kind of gets away from that problem. So you'll see me mix that up depending on if I'm typing or what order, what's going on, how I have things written. But 2+ and +2 mean the same thing. Right? Just so nobody's confused by that. And if there's just plus or just minus, the 1 is implied. All right, so usually any kerning problems can be fixed if you just make your typeset a little bit bigger or switch fonts. But sometimes the font that you've been using for your entire paper causes problems when you get to the end of your paper and you don't want to have to reformat the whole thing. So, especially back in the days when you had to type all this by hand on a typewriter instead of having a computer, or even worse, if you were setting the printing press yourself, it was really, really a pain to have to go fix these things by hand. All right. What's the formula going to be that allows these two charges to cancel out? 1-to-1. So our formula is NaCl, salt, table salt, better or more chemically known as sodium chloride. Do we need to say sodium 1 chloride? Why not? It's assumed that it's 1 because I only wrote the plus there, but why from the periodic table can we know that it's a +1? Because it's in the first column. There's no d orbital involved in the first column, right? All the weirdness that starts happening happens when we get the d orbital involved. Everything in the first 2 columns of the periodic table behaves really, really predictably because there is no d orbital to worry about yet. So everything in column 1 will always be a +1. Everything in column 2 will always be a +2. All right, going back to this slide. If it's in one of these red boxes, that means that you don't put a Roman numeral with it. Because we know that everything in this first column is always a +1 when it's an ion. We know that aluminum is always a +3 when it's an ion. So we don't need to say aluminum 3. We can just say aluminum ion. All right, let's do one more practice from the name back to the formula. How about manganese 4 oxide? So what's the charge on an oxide? What's the charge on the manganese 4? So what's the ratio we need? 1 manganese to 2 oxygens, MnO2.
In your ratios, do you put the cation before the anion?
Yes, good. So whatever has a positive charge gets written first. And then whatever has a negative charge gets written second. That gets a little trickier when we talk about covalent compounds, which is where we're going next, because they're made up of all nonmetals. Michaela? Because the manganese has a +4 charge, which means you need 2 oxygens to cancel it out. So because each oxide is -2, we need 2 of them. So that gives you an overall -4 from the oxides, matches your +4 from the manganese. All right, how do we feel about this? Piece of cake? Yeah, if you took Chem 1, this should be a review. What's the hard part of ionic compounds? Those of you who took Chem 1. We're going there eventually anyway, so you're not saving anything by pretending you don't know what's coming next. What's coming next? Balancing stoichiometry. I was going to go with polyatomic ions. That's one thing that everybody really hates usually. Because that'll be the last time that I tell you just memorize this. It's going to be on the names for the polyatomic ions. So what is a polyatomic ion? Anybody want to take a stab at defining it? Or breaking down the word, even if you didn't take Chem 1. It's an ion with multiple atoms. The atoms put together have an overall charge. So basically, it's kind of like these ionic compounds, but where you don't wind up with the overall charge adding up to 0. And when we talk about covalent bonds, we'll talk about why this happens in more detail. But basically, you get a collection of atoms bonded together that have an overall charge. This whole collection, 1 nitrogen to 3 oxygens, has a cumulative charge of -1. So this whole thing has a -1 charge. It'll still, when we talk about getting our formulas for our ionic compounds, it'll still work the same way. It's just sometimes we're balancing it out using a bunch of these instead of just using, say, chlorides. So what would the formula be for calcium chloride? Calcium's a what? What charge? +2. Chlorine's a -1. We just did that one, right? So the formula will be CaCl2. Now, this whole thing, 3 oxygens to 1 nitrogen with an overall -1 charge, that collectively is called nitrate. If instead of having fluorides, we had nitrate, how many nitrates would we need? Still 2 of them, right? There's just because it's got more than 1 atom doesn't mean that our rules for balancing charges change. Your nitrate's got a -1 charge, so just like with the chlorides, you need 2 nitrates for every 1 calcium. So we just use parentheses, like in math, to indicate that we have this group of things happening, and there's two of them. Right, so I think there's 24 of them. There's 24 polyatomic ions. I have a list of them that I'm going to have you memorize. And then we're going to do another closed book test quiz just on the names and charges of these. So it'll work just like the atomic or the elements quiz, except it's going to be, if I say nitrate, you write NO3 minus 1. Calcium nitrate. So our rules for naming the ionic compounds still don't change either. You say the name of the first ion, then you say the name of the second ion. Just in this case, nitrate, not nitride. Exactly. Right, so we're still just trying to get our charges to cancel out, add up to 0. So if a nitrate is -1 and a calcium is a +2, we need 2 nitrates for every 1 calcium, just like we did with the chlorides. And if we were naming this, we just say it's calcium nitrate, which is why we have to memorize these formulas and charges on the polyatomic ions, because you can't name it properly if you don't know what those polyatomic ions are named. So, but that's looking a little bit ahead. I think we'll talk about polyatomic ions in more detail when we talk about covalent bonds. So it's probably 2 weeks out, that quiz. And I'll have that list for you to memorize when we get a little closer. And then I think that's our last closed book quiz, other than the midterm and the final, right? And that's literally the last time I will say, just memorize this. And it's only because I've not found a better way to get it drilled into everybody's heads that this means nitrate. Nitrate means this. It really just lends itself well to brute force memorizing. All right, this is more practice with balancing out charges to get the formulas. What would the formula for sodium nitride be? What's the charge on nitride? -3. And sodium is +1. So we need 3 of them. So Na3N, sodium nitride. All right. This is more about how this all works. Let's go the other direction. This is also part of why it's so critical that we get our capitalization right on our element symbols, because we could get the wrong compound if we mix up our elemental symbols. So what is RBI? Rubidium iodide. Do we need a Roman numeral on rubidium? Nope, it's in column 1. How about BASE? Barium selenide. Selenium, you drop the ium and put I. So it becomes selenide. Cadmium, do we need a Roman numeral on it? No, that's one of those ones that's always the same, right? It's always a +2. Cadmium, tellurium, drop the ending, put ide instead. Telluride. Just like the town in Colorado. So there's a ski town in Colorado called Telluride. It's where I believe it's where telemarking comes from, actually. Telluride, the town, I believe, was named because there was a mine there before there was a town, where they mined tellurium. Okay. So I always want to go over that one as an example because if you've heard of the town of Tellurium, or the town of Tellurium, the town of Telluride, you might think that you're doing it wrong. It actually is the same name in this case. Cadmium Telluride. Just note for anybody who likes to police grammar, anything like that, if you are hell-bent on applying MLA rules to your science classes, good for you. You don't capitalize chemical names unless it's the beginning of a sentence. They're nouns, but they're not proper nouns. So even though we have to be really careful to capitalize their atomic symbols, the names are common nouns, not proper nouns. All right, and the last one, I already heard somebody do this one. Magnesium bromide. All right, so questions on naming things. Questions on anything? Another D block one? Yeah. How about osmium 8 oxide is a common catalyst in organic chemistry. Osmium is what? OS, and osmium 8 means it has what charge? Plus 8. It's about as large of a charge as you will see on any one ion. It's probably that one. It's pretty close to that. How many oxides do we need then? 4. OS 04.
When you're writing out the names, I know there's like hydrogen dioxide and stuff like that. When would you use like the tri?
So this is as good a time as any. I think we're going to do some math after this, but makes as much sense as any, so I don't have to keep glossing over it. When you have covalent compounds, a covalent compound as distinct from an ionic compound. An ionic compound means you got two ions, a plus and a minus, and they add up to 0. A covalent compound happens when you've got 2 or more non-metals together. Because what's the difference between a metal and a non-metal? Metals give away electrons, non-metals accept electrons, right? So if you, instead of having a non-metal and a metal, if you have 2 non-metals, they're both trying to gain electrons at the same time. And if they're both trying to gain electrons at the same time, the only way you can make everybody happy, the only way you can make that system stable, is if you can put an electron in this 2 orbitals at the same time. What that looks like, so in the case of, we'll look at water first. So how many valence electrons does oxygen have? 6. So it needs to gain 2. It's got 2 empty spaces. So when we start looking at covalent compounds in particular, we start using these dots to represent electrons. So this is called a Lewis dot structure. This oxygen's got 6 valence electrons. It needs 8 to be stable. In fact, we'll color code this. Hydrogen also has a gap in its valence shell, right? And needs to gain an electron. So if you bring a hydrogen atom up to an oxygen atom, they'll put 2 electrons into the same space, one spin up and one spin down. These 2 electrons are in both valences at the same time now. And another way of saying that is that those electrons are covalent. and I'm a little bit embarrassed to say it took me as long as it did, but I'm teaching this for about 5 years before I actually broke apart that into covalence. I never did either. It's just one of those things you get taught. Oh, it's a covalent bond. You don't think about where the word comes from, but literally means into valences. Oxygen still has one more gap here, right? So you add another hydrogen. So for covalent compounds, which is what you get when you have two or more non-metals all bound together, in order for them to be stable, you still want to fill all the valences. But sometimes that means that there's more than one possible way that they can be arranged that satisfies everything. And so, for instance, carbon monoxide, that's not a great example. NO2 is a relatively stable compound. So is NO and NO3. And so is N2O. Those are all stable nitrogen-oxygen compounds. Well, relatively stable. Which means we can't just say nitrogen oxide because we need to be specific which nitrogen oxide is it. So this is where we get those prefixes. Those Greek numerical prefixes. Mono, di, tri. What's 4? Tetra, yeah. What's 5? So there's some of these where the Greek prefixes and the Latin prefixes get mixed up a little bit. Quad is Latin prefix, not a Greek prefix. So we don't use quad, we use tetra. Tetra means 4 in Greek. Which, fun fact, is also where the name for the game Tetris comes from. Even though it's a Russian game, it's actually named based on this because all of the little pieces in Tetris are 4 blocks. Octa, nona, deca, they go past that, but we won't really go past octa very often. In general, mostly we're grabbing things out of this first column. Right, so to specify which of these nitrogen oxides we have, we just specify how many nitrogens and how many oxygens. So for the first element, we don't usually say mono. It's one of those things where if you don't give it a prefix, it's assumed to be 1. So this one, we would just name this as nitrogen dioxide. Now, if it's the second one, there's only one of it, we do specify, so we'd say nitrogen monoxide. And I wouldn't mark you down if you wrote monooxide. We just usually drop that if we have two vowels in a row, 2 of the same vowel in a row, so it doesn't look like monooxide. But if you wrote that, I wouldn't mark you down. Nitrogen trioxide. What is N2O? Dinitrogen monoxide. And I never actually memorized the old school way of naming this. I believe that this one is nitrous oxide, is that they use is laughing gas. Nitrogen dioxide is really, really nasty. It's this reddish, really, really caustic, bad smelling gas that used to be a really common component in smog before catalytic converters were invented. Before catalytic converters, if you got oil and refined it, depending on where that oil came from, when cars burned that gasoline, they had a different color of smog. And so cities, I think LA in particular, had a lot of the nitrogen dioxide in the smog because it was like a yellowish reddish smog. Means it's nitrogen heavy. And we don't have to worry about that nearly as much anymore. One, because cars get better gas mileage now, but also because catalytic converters changed the game when it comes to power exhaust. Yeah. So if it's an ion, that's pretty easy. If it's a covalent compound, as soon as we start making these covalent bonds, the idea of electron configuration kind of goes out the window. We don't have atomic orbitals anymore. We have what are called molecular orbitals that look like atomic orbitals sort of overlapping with each other. But if we have an ion, let's look at sodium versus sodium ion as an example. Sodium is 1s2, 2s2, 2p6, 3s1, right? And sodium ion, 1s2, 2s2. Where are we going to take the electron away? From the highest energy orbital. So we're just when you're talking about the electron configuration of an ion, if it's a negative ion, you just add the extra electrons in. If it's a positive ion, if it's a cation, you take the electrons away from your highest occupied energy level. Right, so I use zinc as an example for this a lot. Yes, that's a good question. So what do we get? So sodium ion is the same as neon, right? Fluoride is also going to have 10 electrons because fluorine has 9 electrons. Fluoride means you gave it an extra electron. So fluoride is also going to be 1s2, 2s2, 2p6. So they have identical electron configurations, but they're not identical in one important way, which is protons. So even though they have the same number of electrons, the sodium ion has 2 extra protons compared to the fluoride. So they can be equally stable, but still have charges. All right, so when we're talking about those prefixes, how do we know if we're going to use those prefixes? When it's a covalent compound, right? When you have more than one non-metal and your charge adds up to 0. If you have a metal and a non-metal, it's an ionic compound. And if it's an ionic compound, you don't use those prefixes because the charges dictate how many of each one you have. Yes. So you can, if you're talking about them in their metallic state, that's actually what's called making an alloy. So you can make an alloy and have metallic bonds forming. If you say added chromium to iron, that's part of how you get stainless steel. Stainless steel is iron, a little bit of carbon, a little bit of chromium, and a touch of maybe some manganese, I think. And that the different types of steel that you can get are basically just different ratios. But in general, you have to take a material science or a metallurgy class before you actually get into a lot of the alloys. We don't mess around with the alloys too much. We talk more about the compounds in chemistry. There are some other cases as well. In my organic chemistry class, we use this compound a lot, which doesn't look like two metals because boron's not a metal, but the equivalent is lithium aluminum hydride. Also does a lot of the same things as sodium borohydride. Let's talk about hydrogen for a second, though. That's a good place to go next. What's the charge going to be on a hydrogen ion? It could be both of those would make sense, though, right? Because hydrogen's got one electron. You can, it turns out. So hydrogen is 1s1. Hydrogen with a minus charge called hydride. And it's 1s2. So then it's the same as helium. It's pretty stable. But you can also have H plus, hydrogen ion. A hydrogen ion doesn't have any electrons. Just nothing. And you could write 1s0, but it's just nothing. So in that case, we actually just call what's left if you have no electrons on a hydrogen, just a nucleus, and the nucleus is just a single proton, right? So a hydrogen ion also sometimes just gets called a proton. When we say we added a proton to something, usually that doesn't mean that we actually went through a nuclear fusion reaction, and it just means that we added an H plus to something. So, for instance, hydroxide is a polyatomic ion with a negative charge. Anybody know what hydroxide does? It's basic. It's the definition of a base for the most part. If you add an H plus to that, what happens to those charges? They add up to 0, right? They cancel. What's the formula become now? HOH, which is frequently written as H2O, water. So proton transfer reactions, where we just move an H plus from one thing to another, actually happen all the time. That's the most common way of thinking about what we call acid-base reactions. Anytime, if you have an acidic solution, it means you've got lots of these floating around. You have a basic solution, you have lots of these floating around. You mix them together, they cancel each other out, and you just get water. It's a bit of a urban myth among chemistry teachers. It's never anybody that I've actually talked to directly, but it's always like, well, I didn't do this, but my teacher did, or so-and-so's friend of a friend. There's always the chemistry teacher that takes sodium hydroxide and adds it to hydrochloric acid, and it makes water and salt. In theory, if you measure everything out really carefully and mix them together, you just get salt water when you do this. But you really shouldn't. So the classic example from back in the 60s, from before there was things like OSHA, was you mix these together and then you drink it to show to the class that how well you made your solutions and how they cancel each other out. But it's one of those things I've never actually met anybody who's done that, but it's always like a friend of a friend tried that.
Isn't that why like writing stuff makes?
That's a slightly different process. It's similar though. So that's a combustion reaction is not an acid-base reaction. It's actually a type of oxidation. But it also, the most oxidized form of hydrogen is water. So you do see, you make some water, and that is why you see clouds forming behind jets in the sky. It's not chemtrails. Chemtrails are not a real thing. It's basically because burning jet fuel produces some water, and it can disturb an equilibrium in the upper atmosphere that causes cloud formation to happen because you add just a little bit extra water when you go through that process.
So why is hydrogen?
Because it's not all the way oxidized. When it's in its gaseous form, it's H2. And so hydrogen, when it's in this state, is stable-ish. But if you put it with something that's better at attracting electrons towards itself, which we'll talk about this property, but basically the closer you get to fluorine on the periodic table, the better those elements are at pulling electrons in. They're bullies, basically. So if you put hydrogen next to oxygen and give it a little bit of energy to start the process, you make water, but you do it kind of an explosive way. Right? That's who's heard of the Hindenburg? Hindenburg is the classic example because hydrogen gas is really good lifting up balloons. It's better than helium because it's half the size. H2 has an atomic mass or has a molecular mass of only 2. Helium is 4. So for the same number of gas molecules, hydrogen actually provides more lift. However, it's almost impossible to keep it from mixing with oxygen. And if you do something like pull too close to a landing tower and cause a spark, your entire airship explodes. You feel it? If we're balanced, we haven't talked about balancing yet, but basically we wind up doing that. 2 H2 molecules and 1 oxygen make 2 water molecules. And then everything backs up to the right numbers. All right. We're not going to go into atomic mass at all today. So we'll finish right there. This weekend, the online quiz, the Canvas quiz will just be a little bit of, here's the name, give me the formula, or vice versa. Just like we practiced today, maybe a little bit of predict the charge. Vinny? Sorry, one more thing. Forgot ionic radius was on the assignment from yesterday. Ionic radius is exactly what it sounds like. Ionic radius just means we're talking about how big the ions are. The difference between ionic radius, actually the ones I just erased are a good example. Sodium ions, neon, and fluoride all have the same number of electrons, right? Which one's going to be the smallest? Why sodium?
Bottom left is like it's less the magnetic. It's like less.
There's more protons for sodium, right? They all have the same number of electrons. Whatever has more protons is going to pull those electrons in tighter. So if they're the same number of electrons, and if you look at the ones on the assignment, they either all have the same number of electrons with different. It might even be these 3.
Yeah.
Right. It's a common reason why that's a really common example. So basically, it's the same concepts as atomic radius, just with different sizes of electrons. It's harder to say because the charge and the number of protons affects it so much. So it's hard to put it as a periodic trend. It's more of just here's a comparison, put them in order. Does that make sense? Yeah.